Let's talk about the size of the nucleus. And, and obviously, the idea is here purely numerical, and as we understand that the first experimental determination of the size of nucleus was made by Rutherford, and and he could calculate the size using the scattering of alpha particles. So he scattered these alpha particles, and what he was able to calculate is the distance of closest the distance of closest approach. And this distance was nearly found out to be 4 into 10 to the power of minus 14 meters. And, and this much of size was calculated for the energy of the particles, alpha particles that were used. The energy was nearly 5.5 mega electron volts. Now, this fact indicates that the size of the nucleus should be of the order of this 4 into 10 to the power of minus 14 meters. And for alpha particles, what you have nucleus, and you're allowing them to scatter through the gold file, and Rutherford was able to measure this distance of closest approach, which comes out to be 4 times 10 to the power of minus 14. And now, for these alpha particles, they have kinetic energies of the order of 5 mega electron volts, and the distance of this closest approach will be smaller as we use the energies of alpha particles more than that of 5.5 mega electron volts. And we have attractive nuclear forces because these attractive nuclear forces will start affecting the alpha particles if their energies are more. They will start to make an impact on these alpha particles. If we make use of energies greater than that of this 5.5 electron volt. And finally, what we will have is when they will be more close to the nucleus, they will experience the repulsive force. So there will be repulsion of these alpha particles and the gold nucleuses that we have in the gold file. So when this experiment was carried out, the size of the nucleus could be measured by using the electrons instead of alpha particles, and for the scattering experiment, and the size, the nucleus size was found to be very linear with the mass number A, as I talked about. This mass number is nothing but number of nucleons, and nucleons are basically protons and neutrons. So what could be observed in the experiment of scattering of electrons was that the volume of the nucleus, it was found that the volume of nucleus is proportional to this mass number. And we can, if we assume the shape of the nucleus to be spherical, then in that case we can choose or the radius of that assumed nucleus that we have. Then we can have 4 by 3 pi r cube. It is proportional to the mass number. And from here we can have r proportional to some constant r naught a to the power of 1 by 3. Now this r naught is an empirical constant for all the nucleuses, and its value is found to be 1.2 times 10 to the power of minus 15 meters, and we can say it is 1.2 Fermi, because 1 Fermi is 10 to the power of minus 15 meters. So this is how the the size of the nucleus, the relation between the radius of the nucleus and its mass number could be obtained, and which gives us the measure of the size of the approximate size of the nucleus. And certainly this are going to increase for those nucleuses whose mass numbers are more. And if I take a simple example here, for example, I have the mass number for a nucleus. Suppose that is 8, and R naught is calculated 1.2 times 10 to the power of minus 15 meters. Then I can find out the approximate radius of this nucleus, and what will be that? That will be 1.2 times 10 to the power of minus 15. And then what I'll have is 8. So 8 I can write 2 to the power of 3 raised power 1 by 3. So this 3 and 3 will go. So the radius of this nucleus will be 4.6 times 10 to the power of minus 15 meters. So I can say that the radius of this atomic nucleus is nearly 6.4 Fermi. So now this is what is this is the basis of understanding the correlation between how to calculate the size, the approximate size of a nucleus.